Okay, well, I mean, something's a little amiss, not quite sure what that is. What I like to do is ask you, what do you guys think about this definition probability? What does it mean to you? Have you, just based on past knowledge, what does that mean, probability? You guys know? What should we say? What do you think? What's the definition of probability? Chance, what's possible. Good. Anybody have any other? What's likely? Good. I like this language here. All of it we're going to talk about. Probability. Give you the cocktail party. If you guys go to a party and the topic of probability comes up, you know what you can tell people? At a party. It could happen. It's a measure of what? It's a measure of chance, ladies and gentlemen. Excuse me really quick. Anyway, it's the measure of chance. Now, what do you think they mean by the word what? Measure. You can assign a numerical value. Okay, so we get to assign a numerical value to this thing called chance. And that's, again, a very, very loose way of describing or thinking about this idea called probability. Now, I got to give you a bunch of definitions and language, because whenever you study any topic, in order to communicate whatever that topic is, you got to have language and vocabulary. Otherwise, you can't even talk. You guys know what I'm saying? Can't even have the conversation. Language. So let's get all the language out of the way so we can start talking about what? Probability. So I'm going to give you guys a bunch of definitions. You're going to write them down. And we start off with the first definition. This is what we call something called an experiment. So we have this experiment. Meaning of the word experiment, that's any process in which an observation is made. Definition of an experiment. Any process in which you could make an observation. Now, observation, so you guys know, this is kind of like a key word here. You say, the key word is an observation. Well, what they mean here by observation, obviously it's things that you can what? See, things that you can hear, things that you can feel. So that word observation doesn't just refer to eyesight. Okay? You can see it, you can hear it, you can feel it. Like hot weather or rain, you can feel those things. Okay? You can even feel, these tiles fall and hit you on the head. You guys know what I mean? These are all thought of as really observations in general. Yeah, I've seen it happen, by the way. It's happened. It happens. Tiles are glued to the ceiling and they fall. Where did you see it? Oh, wow. One of these tiles? Good thing they're light, if you guys didn't know. Kind of I hate to, yeah. I hate to break the news to you. It's in order to sue and get rich, something serious really has to happen. So lightweight, it's like foam falling here. Anyway, experiment. Any process in which an observation is made. It's called an experiment. For example, these are my favorite examples. You can flip a coin, ladies and gentlemen. So when you flip a coin, can you guys tell me what can you observe? Yes, it could land on a heads or it can land on a what? Tails. Those are the observations. Okay, so you're going to have to be familiar with some of those ideas here. Flip a coin. Believe it or not, what's kind of analogous to flipping a coin is you can have a child. And we're talking about really what was referred to years ago as gender. When you have a what? Child. Okay, what do you think? What do you think they mean by that? You can have either a what? Boy or a girl. Outstanding. These are the observations, ladies and gentlemen. Okay, some standard kind of questions here. Another kind of situation, example of an experiment, is you can actually roll a die. Does anybody happen to know what a die actually is? What's a die? Yeah, exactly. It's that cube you roll, right? Now, notice what you said. It's a cube. It wasn't cubes. Because sometimes people don't know. There's a difference between the word die and dice. What are dice? It's more than one of those cubes, 2 or 3. You ever hear the phrase they say roll the dice? It could be 2 of them or you can have 3. But if it's a die, there's only one. Only one. So what could you see when you roll a die? You can see a what? You can observe a 1, good, a 2, a 3, a 4, a 5, and a 6. These are the things you can observe. These are all examples of what? Experiments and those things known as observations here, okay? So these are the observations for each one of these experiments. So you go, oh, heads or a tail when you flip a coin, boy or a girl. Roll a die, it could be a 1, a 2, a 3, a 4, a 5, or a 6. Nice, good. Those are all experiments. Now, I'm going to kick this up a little bit, okay? I'm going to kick it up. You say, what do you mean I'm going to kick it up? You can actually have, ladies and gentlemen, 2 children. And if you have 2 children, we're going to describe what you can observe in terms of the gender again. Okay? This is all in terms of the gender. Now, this is a little bit more complicated. Would you guys agree? Now, I want you guys to note here. Sometimes when you have more than one item, there's a little secret, there's a little key. Think of them as one at a time. You have these children one at a time. So if we have to describe what's called the gender sequence, because there's now 2, put that word down here too. Think of them as one at a time. Now I'm going to share with you guys a little trick here. It's called a tree diagram. Okay? Since you're having your children one at a time, what's the gender for the first child? It could be a what? Boy or a what? Girl. You said, Mr. Judge, I already told you that one. I say, I know. This is for the first child. Okay? Now, after the first child, since you're having them one at a time, I guess you have the second child. Is that right? So, okay, for the second child now, what can you have for the gender? If the first child's a boy, what can happen on the second child? Again, you get a boy or a girl. Is that right? And that's for the what? The second child. What if your first child was a girl? On the second child, what could you have? Boy or girl. This is called a tree diagram. It's like saying that you have a tree on its side. This is extremely helpful, ladies and gentlemen, in finding gender sequences for, really what's called multiple items here. Okay? Now you say to me, what do you mean the gender sequences? Follow the branches. Follow the branches. If I follow the branches, what do I get? Don't I get a what? First child's a boy. Second child's a boy. What do we call that? BB. Okay, you guys okay with that one? Well, you got to, when you teach people a subject, in my opinion, you got to build the layers. It's kind of like cooking. Anybody here a good cook in the room? Oh, you are? What's your best dish? All of them are good. So if somebody says to you, like tonight you get home and your family goes, hey, could you make, fill in the blank, what are they going to say? Are you sure? How do you make video? Because it just so happens I'm into making video myself. That's why I ask. You can't give the secret recipes? It's a process. Do you collect the fat and you put the fat on the grill when you cook the shao? You don't do that either? When you do the shao, that's how you do video. That's not the way to do it. We may not. They do a different video, huh? Ooh. Excuse me. Interesting video. Maybe we don't even know what we're talking about. Are you talking video tacos? All right. Anyway, I had some video tacos last week after class, like I told you guys. Teddy's Red Tacos there in Whittier. They're just okay. They're not great, are they? That's what I thought. I'm like, these guys, they should have put some salt in it. They didn't have salt. They're so bland. Yeah, they're very bland. Anyway, we'll maybe Google it and show you guys. Video is a whole thing. Do you guys even know what we're talking about? Anyway, did she make it with a colame? What is it? The kosame? Sorry, I can't even pronounce it. Kosame. Did she do it with that too? Oh, good. That's what I'm saying. Is like some people, what they do is, what they'll do is they'll put the meat overnight. They separate the meat from the liquid, and overnight in the liquid, what happens? That fat goes on top of that layer. Then they scrape out the fat. You guys know what I mean? Then that fat goes on the grill when they make the tacos. Anyway, I was like, oh, okay. The what? Never seen video with noodles. That's new. Is that right? Thank God. Boy, what's this? Girl. That's the second gender sequence. Follow your branches. Girl, what's this? Boy. GB. Do you guys know what that means? You're having a girl first, then a boy. Yeah. And then you have what? Girl, girl. What you guys are looking at is all the what? Yeah, I got 1, 2, 3, 4 outcomes when I have 2 children. This is an extremely important process. So we're kicking this thing up. All right. Should we kick it up even further? Let's do one more here with this. You're now going to have what? 3 children, ladies and gentlemen. I want you guys to think about this. Okay, you seen that we just did here? Have your children, here's the key. One at a time. One at a time. How can we extend this idea for gender sequences when you have now, what, 3 children? Here's what I'm saying. Here's your first child. Boy, boy, or girl, girl. Here's your second child, ladies and gentlemen. See what I'm saying? What if I said to you, because this was a test question once, 3 children, what's the gender sequence here? Use a tree diagram. So I'm going to ask you guys here to try that out with gender sequences. Of course, you're going to do it one at a time. So I'm going to say you're going to start here. See if you can extend this tree diagram process for now 3 children. Okay, this is a learning tool. I'll give you guys some time here. Try it out. Okay? See what you guys get. All right, ladies and gentlemen, this was on Exam Watch. You guys are going to see some of this a little bit later, but I just want to let you guys know, here's how you do this. It's not hard. Think of having kids how? One at a time. Good, good. So for the first child, what could you have for the gender? Boy or girl. You guys okay? That's for the first child. Easy breezy, lemon squeezy. Now you're going to have the second child. You're going to do it. We're going to have them one at a time. For the second child, what do? You're going to have a what? Boy or a what? Girl. Now, what if your first child was, because you're working on the second, what if your first child was a girl? Same thing. You know, boy or girl for the second child. Is that right? You see what I'm saying? Now, the third child, how does that look? Okay? For the third child, you see all of these? outcomes here. Notice this for the third child. For the third child, you can have a boy, you can have a girl, is that right? There's no memory of what your child is as you go have them. BG, BG. So this is a tree diagram, ladies and gentlemen. And then what do you do now with the branches? Follow them. What do I mean by that? B, B, what? B. B, B, B. Yes, is that easy? You guys see what I'm saying? So here's the gender for your first child, B, in orange. And then you're going to have the gender for the second child here. Finally, the gender for the last child. Just follow all those branches here. Well, this will be B, B. Now this will be what? G, yes. So it'll be boy, boy, girl. Okay, follow the branches. What will you get next? What's the next one? Yep, BGB. See that? Then BGG. Yep, then G, BB. Right? See this here? G, B, B, and then G, B, what? G. Then G, G, B, and then G, G, G. So these are the gender sequences, ladies and gentlemen, when you have what? 3 children now. That's as far as it goes that we do with the tree diagram, though. Not going to have 4, 5, 6. It's not going to do that. Just up to 3. Okay, but these are all experiments. Okay, in the beginning for probability, we got to give you guys a bunch of language now. A lot of definitions. Now, after you guys have the definition of an experiment, I'm going to give you guys a definition of what we call the sample space. Okay? And it has a symbol, capital letter S, for sample space. I usually put this in red because it's kind of an important definition, the sample space. This is the list of all possible outcomes. So, when you say list of all possible outcomes, okay, or I should say, yeah, that's really formally the set. But a set, in case you guys didn't know, a set is a list. And we name our sets with capital letters, and then we use these curly brackets. You guys remember from sets? You guys ever see that before, these curly brackets? Set notation. What I've been doing here for you guys all along, you see this for this first experiment? This is actually the sample space. You say, why? Those are all the possible outcomes for an experiment. All outcomes. You flip a coin, it could be heads or tails. We just put it this way, symbolically. This is the sample space for the experiment of having a child. Remember, a child means one child. This is a sample space for rolling a die. Okay, this is the list of all possible what? Outcomes. Yes. And then you said, what about this? S here, the sample space, we could list it and we write it down horizontally, like BB, BG, GB, and GG. Here's my sample space. The list of all possible what? Outcomes for an experiment. There's S. And then finally here, this list, well, I'll just do it like this. I'll keep it this way and put commas. I'll keep it vertical. We can kind of do that. It's not that big a deal. And then we call that sample space, the list of all possible outcomes here. Okay? And I should have given you more language. This is for an experiment. All right. We're almost there. And then now I have to give you this kind of definition, another definition of what we call an event. And it has a letter as well. Definition of an event, very similar to sample space. It's a set. And that's going to be, well, we call that a subset of the sample space. Okay, being a subset. You guys know what a subset actually is? It's a sublist. We have this kind of notation. Okay, so in other words, E is a subset of the sample space S. So any subset of the sample space is called an event. Okay, so do you guys happen to know what is a subset? Just kind of a picture. I'm going to draw a Venn diagram. This picture here is worth 1,000 words. In other words, if you had everything in the sample space S here, every outcome, in the sample space, this is what we call a subset of the sample space. Just as a picture. So you might say, what does that mean to be kind of a subset here, right? What that means is this: every item in E is also in S. So these are all the items that are in E. They're contained inside the sample space. They have to be contained. And that's what we call a subset. Okay, it's defined to be our event. So I'll give you an example of it. It's a very simple example. You look at this definition, it's a highly technical definition. You do need it, and you'll see why. But what I like to do is I like to go back to rolling a die. It's going to go back to this here to give you examples of events here. Okay, let me give you an example of an event, okay? So I'll just going to say, I'll write it as a fact. I'm going to say the following are events. Okay? You're going to roll, for example, 1. You're going to roll a 4. So I'm going to use this subset or this set notation, these brackets here. Okay? So if I said to you, what does it look like to roll a 4 here? Go back to the sample space here. Do you see a 4 anywhere in the sample space? You do? Where is it? Right here. Isn't that the 4? Okay, so ladies and gentlemen, guess what? This is the event of rolling a 4. Okay, the word 4 aligns with the number what? 4. Does that make any sense? Does that kind of seem simple? Notice the 4 is contained in the sample space, right? It's an event. So we're going to look at the sample space. How about this event here? Let's say you roll a 1. Okay. So go back to the sample space. Is there a 1? How do you know? This is what it is right there. This is the symbol for what? The number 1. You guys okay with that? There's a language associated with these symbols. Does that seem easy? Easy breezy, lemon squeezy? Not too bad? Okay, let's look at this next event, number 3, because we're kicking it up. How about if we say you roll a what? An even number. So here's the thing now. Yeah, you're going to have to know a few things here. What do you think you have to know? What's an even number? What are they? Go back to the sample space. Is that right? Where do you have the even numbers? Where are they? 2, 4, what else? 6. Why don't I list 8? 8's an even number because it has to be contained in the what? Sample space. That's why it has that definition. Any subset, this is E, has to be contained in the sample space. This is like the context. So what I'm saying is you don't list the 8, you don't list the 10, you only say 2, 4, and 6. Yes, 8 is even, but this is not a subset of the sample space. It won't be contained in there. Is that simple? What if you say an odd number? Right? So go back to the sample space. What numbers are odd? Yeah, but and you say, well, 1, 3, 5. What about 7? 7's odd. It's not in the sample space. Good. What about 9? 9 is odd. Not in the sample space. Outstanding. So here, these are all describing events. 1, 3, 5. You're done. Okay, these are examples of events. Number 5, a number less than 3. Now, ladies and gentlemen, here we go again. You're going to have to describe numbers that are now what? Less than 3, but they have to be in the sample space. So which numbers here are less than 3? Do we include 3? No. Outstanding. Do I see what I'm saying? Where it's language and process? Language and process? So we just put 1 and 2. Okay. How about if I said this? Question number 6 here. No more than 3 now. No more than 3. These words, no more than 3. Do we include 3 for no more than 3? Yes, we do. Because no more than 3 means 3 are what? Are less. So it's the numbers 1, 2, and 3. No more than 3. How about numbers if they say more than 4? Okay, you guys see how this is what I'm saying. Language is a very big deal and it's a very, very big part of all of this course. You got to know what more than 4 is. So for more than 4, what do? It's going to be what? 5, what else? And 6. More than 4, you do not include what? 4. So we say 5 and 6. Okay, how about question number 8 now? At least. At least 4. What's the meaning of at least 4? Right, it's 4 or more. So you're going to say 4, 5, and what? 6. Okay, so you go back to that sample space, 4, 5, and 6. All right, what do you guys think about that? Is that pretty good? Pretty simple so far? Okay, now another definition and you're almost there. Definition of what we call the cardinality of a set. And for me, cardinality, you know what I think of? Sometimes I think of like a set if you go to the grocery store. Right, here's it. What do you get at the groceries maybe? What do you get? Lamb? Oh, ham. I'm like, woo. What else do you get? See if I can get this charged again. Oh, it's 0 charge. Okay. Ham. Yes. The event? Yeah, go back. Take a look. Any subset of the sample space S. Down here? Okay. You okay? You good? All right. Okay, cardinality. Think of this. You go to the grocery store, what do you get? You say, okay, I get ham. What else do you get? You get what? Eggs? What else? Milk, okay. What else do you get? Bread. Okay, anything else? Okay, you say apples and maybe some beets, I don't know. Okay, so you guys see this. This is a set, by the way, grocery list, right? The cardinality, if you ever go to the grocery store, isn't there a special line you could get in? Well, there's like an express line. What does the express line say? 15 items or less? That's not so expressed. It used to be 10 items or less. now it's 15 items or less, right? So if I said to you this, the cardinality, that's defined to be simply this: the number of items on A. Cardinality of set A. This is the definition. The notation is functional notation. This is N of A. So what I'm saying is I'm going to move this over here. N of A equals what? The number of items on A. It's a cardinality. So if I had to count the items in my groceries list, G, how many items are here? Say 1, 2, 3, 4, 5, what? 6. There are 6 items on the grocery list. So N of G is what? Is 6. Well, you're counting. So there's two different, this sample set, yeah, you can think of it as sample size too, right? So there's 6 items on the list. You're just counting how many items are there. Now, ladies and gentlemen, just to see if you can practice this, how many items are on this list here? What's N of E here? 3. Outstanding. That's important, ladies and gentlemen. 3 items are in this list. That's good. How many items are in this list? 2. Good. You're just counting. How many items are over here? N of E here is what? Is that 3? How many items are over here? There are 2. All right. How many items are here? 3. Good. How many items are over here? 3. Okay. How many items are in each one of these here? N of E is what here? Good. What's N of E over here? Outstanding, ladies and gentlemen. If you can count the items in the list, that's a big deal. Okay? Counting is a big deal. How many items are in the sample space here? What's N of S here? N of S, what's this? 6 items. Outstanding, ladies and gentlemen. You're on your way. Here we go. 6. How many items are in... Let's go here. How many items are in this set here? 4. Good. We already know that one. How about this? Having a child. How many items are in S? 2. Good. It's a big deal. And how many items are in this one? N of S is also what? 2. Good. Okay, ladies and gentlemen. And the 3-child one, did you count over here? How many items are in S here now? Did you count this one? Having 3 children, how many gender sequences are there? How many? Let's count. 1, 2, 3, 4, 5, 6, 7, what? 8. So believe it or not, this is the hard part in some ways. Okay? Generating the sample space and counting items. Generating the event and counting items. And that's it, because here's your definition. This is the definition of the day, ladies and gentlemen. Definition of what we call the probability of an event. Here it is. Okay, it has function notation as well. That's P of E, probability of E. So on the left side, we read this way. Probability of E. That's on the left. So the probability of E is N of E divided by N of S. This is your probability definition here. So it's really just 2 numbers. It's a numerator and it's a what? Denominator. That's a fraction. Okay, so I want you guys to notice this. This is a fraction. Probability of an event. So I'll give you guys a few seconds to write that down. Because now we get to see an example here. So this is the probability of an event. Okay, so here's going to be the deal. Here's how you see your first example of a probability. So they're going to say something like this. They're going to tell you the experiment. You roll a die. Okay? Comma. What's the probability of rolling a question 1 of 4. Okay, question 2, rolling a what? A 1. We'll see. What do they give you here? What is this called here? You guys know what this is called? This is called an event. Those are your events. So you can only take probability of an event. You say, how do I know? Because what do they give you? This is in the definition, the probability of an event what? An event E. So they're going to give you the event in words. So you say, what word? What's the word for rolling a 4? Right? You see this 4? What's in the event? 4. Good. You see this 1? What's in the event? 1. There you go. Does that look familiar? It should. But these are probability questions. What's the definition? Right in here. See, you'll never answer a probability question without knowing the definition. Very often when people say to me, Mr. Judge, I don't understand the question, this probability question, you know what the real problem is? They don't know the definition of probability. What's it going to be? What's the definition? I need a numerator. What's this? N of what? E. I need a denominator. What is this? N of S. What is S anyway? It's your sample space. You say, is it all the way over here? Yes. It's right here. And in fact, in all honesty, we have all these answers already. We already have the answers. So it's just putting this together. So yes, you have to consider the sample space and that there's 6 outcomes. Okay? So for your first answer here, the denominator is 6 because that's what N of S is. Right? You're using this definition here. N of S, the denominator is 6. What's the numerator for each one of these questions? 1 and what? 1. Okay? Why is it 1 and 1? How many outcomes consist of looking like the number 4? 1. How many outcomes consist of looking like the number 1? 1. There you go. 1/6 and what? 1/6, ladies and gentlemen. Here are your answers. So the chance you roll a 4 is 1/6. It's a fraction. Chance you roll a 1 is also 1/6. All right, you guys okay with that? Is that easy breezy? What if I said this to you, question number 3, what's the chance you roll a 3? Right, you're going to have to know, what does the event of rolling a 3 look like? The single 3. Okay, how many outcomes are here? 1. How many outcomes are in the sample space? There you go. It's also 1/6. These are all probability questions, ladies and gentlemen. 1/6. You start from the beginning. You start simple. What's the chance you roll an even number? Do you know what even numbers look like from the sample space? What is E? Yeah, it's what? 2, 4, and 6. Okay. So it's going to be 3 out of what? 6. Doesn't that reduce to 1/2? So ladies and gentlemen, probability is 1/2. Yes, you have to reduce your fraction. Right, 3/6 becomes 1/2. And there you go, ladies and gentlemen, that's the deal there. How about question 5, an odd number? Right, you got to know 1, 3, and 5 are what? So probability will be 3 out of 6 again, which reduces to what? 1/2. see earlier here for some of these events, we said, okay, how about even number, odd number, a number less than what? Number less than 3. In fact, yeah, let's copy that. So if I go up here, how many outcomes are less than 3 again? 2 out of how many? 6. What does that reduce to? It's 1 over 3. There it is, ladies and gentlemen. 1/3. You got a 1 out of 3 chance of rolling a number less than 3. What about this one? If this were a probability question, this is 3 out of what? 6 also reduces to what? 1/2. So these are probability questions, ladies and gentlemen. Now we're changing them to probability. More than 4. How many 5 and 6 are more than 4? This is 2 out of how many? 6 reduces to 1 what? 1/3. Probability roll a number at least 4. That's also going to be what? This is going to be what? 3 out of 6 again? Reduces to 1/2. Okay, is that easy? What do you think? Pretty simple? Can't see. Might want to look at all those seats up here in front if you can't see. That's like the best seat in the house. I could lend you my glasses. They won't work. But you could sit right up here. Or you can even sit right here. Even better. Struggle? You want to struggle? I don't. Only young people like struggling. I don't like struggling. Let's give you guys an example. Let's go back. Let me get the sample space here. You're going to have 2 children here. So I'm going to get this situation. Okay, so you're going to have 2 children. Another example. Example of our probability definition. Okay, now I'm going to ask, what's the probability of having question 1, no girls? Question 2, 1 girl. Question 3, 2 girls. Question 4, no more than 1 girl. So let me get out here the sample space, right? So this is going to kick it up a little bit. So if I ask you guys this question here, how do we figure this out? You got to look at the sample space, is that right? So which one of these outcomes corresponds to having no girls? You know what I do? You see BB? How many girls do you have? If I said, look at this first outcome, BB. How many girls are here? Good. BG, how many girls are here? Good. GB, what would you guys say? 1. What about GG? 2. Okay? You're counting girls. Now, which outcome consists of having no girls? The first one, right? So what would you say for a probability? 1 out of, how many outcomes are in the sample space? 4. Good. I'm going to color that red. We already got N of S was 4. Okay, you guys okay with that one? So this is how you answer those kind of questions. How about one girl now? You say, which outcomes correspond to having one girl? Right in here. BG and what? GB. Because remember, BG, you had a boy, then a girl. GB, you have a girl, then a boy. The order is there. So what's this fraction going to be? 2 out of the 4 in the sample space, which reduces to what? 1/2. So ladies and gentlemen, this is the probability, and this is the probability for 1 and 2. So ladies and gentlemen, this is how you handle these having 2 children questions here. Huh? It's what? Oh, yeah, we're going to have a break. I'm looking at, you know how many Teddy's Tacos there is? Darn it. You got one in Echo Park, one in Almani, one in Whittier, one in Southgate, one in East LA, Venice, Inglewood, Downey, Anaheim. Oh my God. Your mom has to do, she's to start her own taco place. All right, this is number 3. Having 2 girls. Yeah, let's look at the outcome here. Isn't that 2 girls? There's 1 out of what? 4 outcomes. Remember this, you have to have N of S. There you go. 1/4. There it is. And then, what about the last question? Do you guys know what no more than 1 means? What's no more than 1? 1 being the max. It's 1 or what? 1 or none. Is that true? Okay. Yeah, 1 or none. So you say, well, what's that going to be here? Well, how many outcomes? 3 outcomes out of 4. So this probability is 3/4. There it is, ladies and gentlemen. Yeah. Well, that's 2. To say no more than 1 girl, you're having 1 girl or no girls. Right? 1 is the limit. You're thinking of question 5. Question 5 is, what if they say you had at least 1 girl? Let me get this here. At least 1 girl. So what does at least 1 girl mean? 1 or more girls. Okay? 1 or more. Now you say, well, what's 1 or more? It's 1 or 2. Is that right? 1 or 2, because that's 1 or more. So how many outcomes there? 3 out of 4. So remember, it's always out of 4 in this example. That's N of S, because we already answered that question. These are your probabilities, ladies and gentlemen. Easy breezy, lemon, what? Squeezy here. So that's our start. Now, we're going to look at a lot of different examples here, by the way, of probability questions, because you really want to look at them, You got to see different examples. Okay, so far you only looked at rolling a die. You've only looked at having two children. We're going to look at different examples so you can have a good feel for probability using this technique. Okay, it's language in process. But we're going to take a break, ladies and gentlemen. So I'm going to start. Take a break. And let's get out the clock here, okay? You guys can go to McDonald's, or you can do what? Go to Teddy's Tacos. What happened here? Go to Teddy's Tacos if you like. All right, we'll see you guys in a bit. Look at this. Hot sauce is pretty not bad. See, the thing, I think the real key that people really overlook is the hot sauce. If you got a real good hot sauce, forget it. That makes a lot of things. It makes up for a lot. And if it's a really bad hot sauce, you're like, oh man. That's my personal thing. The hot sauce can really make it. It has to be flavorful and hot. Well, it's like a red chili. Like if you had a King Taco, you know that red chili. Usually, what it really is tomatillos, onion, garlic, salt with some chili peppers, and that's going to give you a good hot sauce. That's a typical hot sauce. There's a lot of places that do it fresh. The what? The green one? It's pretty much the same, because the green comes from a tomatillo. But it really depends on the chili pepper you use. Habanero. Yeah, you could use those. You can use those dry. What do they call those small dry ones? That you get. You could use those even, and it makes it orange. A lot of people do that, and you don't even get like a habanero. But I'm pretty sure that's what they do at that taco place I go to. Pretty sure they do that one. There's another place there by Garfield High School, a fish taco place that does the same thing with the hot sauce. It's really flavorful and hot. It makes your fish taco, because it has to be a flavorful hot sauce. Ask your mom; she'll agree with me. Hot sauce. Does she make fresh hot sauce? Exactly. Yep. Exactly. I hear you. I get it. That's we can do that. If you could pull that part off, you've done a lot. Yes. That's my point. See, that's what Teddy's Tacos is missing. Good flavor, hot sauce. If they did that, it would have been, it would have been good. Cutting corners. You can tell. You can tell. I'm going to have you guys try one here. You're going to have 3 children. This was actually a test question. This was the test question. You're going to have 3 children. No boys. Question 2. 1 boy. Question 3. 2 boys. Question 4. 3 boys. Now I'm going to change this to all boys. Question 5. More than 1 boy. Now say question 6. At least 1 boy. Now I'm going to give you guys a sample space, because remember, we did the tree diagram. This is why I have you guys do the tree diagram. And my sample space is still kind of, I'm going to have to fix this a little. So this one was a test question once. So I'm going to kind of do the sample space here. I'm going to put it down here. S will be BBB, comma, BBG, BGB, BGG, and then GBB, GBG, GGB, GGG. Okay, so we're going to give you guys some time to do this one yourself again. Let's see how it goes. And, all right. All right, ladies and gentlemen, let's try these out here, okay? Notice the question, though. What did they say here? They're asking, no boys, is that right? One boy, two boys, and so on. So now they're referencing boys. So, BBB, this first outcome, first gender sequence, how many boys do you have here? Good. So put the 3. What about BBG? 2. Good. What about BGB? 2. BGG, how many boys? 1. Good. Now, how many boys over here for GBB? 2. How many boys now? GBG? 1. GGB, how many boys? Finally, GGG, how many boys? 0. Okay, so we're gonna label these events that we're looking at because it's going to enable us to answer our questions here. So for N of S, though, how many outcomes are in the sample space? You guys know? How many? 8. Outstanding. 8. So every one of these answers divided by 8, 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 divided by 8. This is the denominator in the probability questions. Okay, so I just want to make sure you guys can see that and know that, because all we're getting now is the numerator. Is that true? So how many of the 8 outcomes correspond to having no boys? That's question number 1. How many of these 8 outcomes have no boys? It's only one outcome, the GG what? G. So ladies and gentlemen, the probability is what? 1 out of 8. There you go. Probability of having no boys is 1/8. Outstanding. So now the next question, probability of having 1 boy, we're going to have to go to the outcomes that correspond to having 1 boy. What are they? BGG, there's 1 boy here. GBG, 1 boy. GGB, 1 boy. How many outcomes are there? 3. So this probability will be 3/8. Outstanding. Okay, good job. All right, you guys okay with that? Not so bad. 3/8, okay. Okay. What about the next one? 2 boys now. So let me erase this, this, this. Which outcomes correspond to having exactly two boys? BBG, BGB, and then GBB. It looks like there's going to be another what? 3 outcomes. So this will be 3 outcomes out of 8. 2 boys. Here we go. All right, now what about all boys? What does that mean to have all boys? Do you guys know what that means? If you're having 3 children and they're all boys, what are they? BBB. Okay, so this is BBB. So this is the all boy answer. How many outcomes consist of having all boys? Only 1 out of the 8. So ladies and gentlemen, that's your probability. It's 1/8. So there you go. All right, look at question number 5. What does 5 say? More than 1 boy. What does more than 1 boy actually mean? It means you can have how many? 2 boys? Or what? 3. Outstanding. More than 1 means 2 boys or 3. And so how many outcomes are there again? 4. So you might say, oh, hey, there's 4 out of 8. That's right. But what does that reduce to? It's 1/2. So ladies and gentlemen, the probability is 4 out of 8, but it reduces to 1/2. You always want to give the what? The reduced fraction answer. So 1/2, that's question number 5. 1/2. Okay? So this was test questions once, by the way. At least 1 boy. What does at least 1 mean? 1 boy or what? More. So at least 1 means 1 boy or more. So let me go to the events here, the outcomes that have, this is 1 boy, exactly 1, or more, 2 or what? 3. So how many outcomes are there? 7. 7 out of the 8, and ladies and gentlemen, there you go. Outstanding. This is how this works. Okay, can you see that there? You guys see what I'm doing there? And like I said, that was a test question once. I gave the 3 children. I've given 2 children. You know, for 3 children again, you want to remember that the sample size is 8, and that's why you're dividing by 8 with all these answers. So easy breezy lemon squeezy. Okay, well, let me introduce you to what we call a standard deck. It's a standard deck of cards. You go, oh, here's those card questions. What's a standard deck, by the way? It's a regular deck, but what do? Throw out the jokers. You throw out the jokers. That's a standard deck. So what I'm going to do now here is introduce you guys to this standard deck, because it's a very, very rich environment, I would say. And what I'm going to do here is I'm going to bring it in. Sorry, let me go back here. I'm going to bring it in for us. And I want you guys to copy that picture. It's important to copy this picture. I'll give you time, because we're going to use this environment. I don't know what I did. We're going to use this environment here for quite some time to answer probability questions. Is that right? That's a standard. So anywhere in the nation, you take this course, you start talking about probability, Guess what they'll have? The deck of cards kinds of questions. High school as well. Everywhere you go, it's a very rich environment. So this is why it's there. So how you really learn this is to copy that picture, and then we'll talk about the picture. So let's give you guys some time to copy that picture. Okay, so then we'll talk about it. Okay, you guys get that picture copied here so we can start to discuss this so we can work with probability? Let's see this here. You guys see the first row? What do you see in the first row? Well, let's read the first row together, okay? We start to read that. You see a 2 of heart. In other words, you see hearts in that first row. Is that right? So numerically, it starts with a 2, and then it's a 3. It goes all the way up to 10. That's called the 10 of hearts. What comes after the 10? You see the J? What's that? That's a jack. That's not a joker. It's a jack. We threw out the jokers. You see a queen. You see a king and an ace. Okay? You guys okay with that? So you got the first row is hearts, and then you duplicate everything you see, but the second row you have a different shape in the middle there, right? What's the shape in the middle now? Those are diamonds, okay? So it repeats the pattern of a 2 of diamonds up to a 10 of diamonds, jack of diamonds, queen of diamonds, king of diamonds, ace of diamonds. What's the third row? What is that symbol? That's a club, yes. The third row is clubs, right in the middle, the third row. Those are clubs. Okay, so you have a 2 of clubs up to a 10 of clubs, and then the same jack, queen, king, and ace of clubs. You got, what's the last row? Spades. Those are spades. 2 of spades up to a 10 of spades. A jack, queen, king, ace of spades. Now, I also want to say, where do you guys see the ace? It's above a king. It's to the right of the king, okay? So, standard deck, throwing out the jokers. If the ace is to the right of a king, we call that ace is high. If the ace is below the 2, what do we say? Ace is low. So in this picture, since the ace is above the king, I'm going to notate this. I'm going to say to you guys, here in this picture, ace is what? High. Okay? Standard deck, throw out the jokers. Ace is high. Now, something important here, okay? I'm going to start to kind of make some notes here for it. N of H is the number of hearts in the standard deck. Okay, it's the cardinality notation here. N of H. How many hearts are there? How do you know there's 13 hearts? Exactly, that's how I look at it. It's going from 2 to 10. And then if I said, how many cards go from 2 to 10? It's not 10, it's what? 9. And then you add the jack, queen, king, and ace, which is 4. 9 plus 4, and you're right, 13 hearts. Outstanding. That's how I look at it. And then diamonds, I would say, isn't that N of D? Okay, how many diamonds are in the deck? 13. Same number. What comes next? N of spades, I put SP for spades. How many spades are in the deck? 13. And then N of clubs, N of C. How many clubs are in the deck? Okay, does everybody agree with those values? You guys okay with that? Okay, now, how about this one? How many cards are in the sample space? 52. How do we know? 13 times 4 is 52. There you guys go. That's right. Okay, now let's see if this gets a little bit more harder. How many cards are red? I'll say, what's the number of red cards in the deck? Well, isn't half the deck red? So half of 52 is going to be what? 26. This is the number of red cards. How many cards are black? The other half, 26. In other words, if you guys notice, the hearts and the diamonds are red, so there's 26. The clubs and the spades are black, so that's also 26. Okay, easy breezy so far, just studying that deck. Let me say this. How many aces are in the deck? Well, how do you know there's 4 aces? Where are the aces anyway? Isn't it the column on the right? Okay, see, let me see if I can move this. I guess I can't. The column, we have the ace of hearts, ace of diamonds, ace of clubs, ace of spades. So, ladies and gentlemen, 4 aces. Okay, just to do some notes. How many kings are in the deck? Also what? It's the second to the last column, right? So that's going to also be what? 4. How many queens are in the deck? 4. How many jacks are in this deck? 4. And then this is going to be, I'm going to say N of F. This is going to get people. What do you think that F stands for? Number of what? Face cards. Yes, the number of face cards. So you see this little F that I just put there? That F, they say, what's N of S? This is how many face cards. Now, if you said to me, what in the world is a face card? Do you guys know what a face card is? It's a card that's not a number card. It's a card that has really a face on it. And if you look at this, you go, I don't see any faces. And you're right, there are no faces. But the jack, there's a picture of a gentleman they call a jack. I don't even know what a jack is. That jack has a face, though. It's a picture of a guy. The queen, well, I know what a queen is. The king, I know what a king is. An ace, well, that doesn't have a face. So the face cards are the jacks, the queens, and the what? Kings. There's 3 of each type, so 3 times 4 is what? So, ladies and gentlemen, there is 12 face cards, just so you guys know. So, like I said, we're looking at all this, and we're doing what? We're notating this. And this information all comes from looking at your what? Standard deck of cards, okay? So I'm going to remove that here, put it to the side, because they like asking probability questions with this information. Here's how they'll word it, though. They're going to say the following. Right? They'll say, you select a card at random from a standard deck. What's the probability of selecting, question 1, a king? Question 2, a heart. Question 3, a king of hearts. Now say question 4, a red king. Okay, so let's try to answer these 4 probability questions here to get started with. And yeah, they're kind of standard probability questions because they're very rich in, I should say, what? Very rich in different kind of questions you can ask. So, okay, let's do it this way here. Let me give you guys every detail. What I write down here is P of K. Okay, this is function notation. The definition is the number of kings in the deck divided by the number of cards in the deck. So, how many kings are in this deck? Yeah, so the idea is that you got your picture there, you can visualize that, right? You say, there's 4 kings out of how many cards? 52. Okay? 4 out of 52 here. The second to the right column, 4 Ks. Now that reduces. You guys know what that reduces to? It's 1 out of 13. Okay, good. So this is the probability, ladies and gentlemen. The chance you select a king is 1 out of what? 1 out of 13. There you go. Okay, what do you guys think? Is that okay? Pretty simple, right? Now that you look at the deck of cards and you study it, it's not too bad. At first you think, wait a minute, right? It isn't too bad. Let's do the next question. Probability to select a heart. So in other words, P of what? H. Right. So you have to find the number of hearts out of the number of cards. So how many hearts are in a standard deck? How many hearts you guys see there? 13 out of 52 cards. Okay, remember N of S, 52. N of S, this is my N of S, 52. So 13 out of 52, what does that reduce to? What? Yeah, it reduces to 1/4. So what I'm going to do here is I'm going to move this down. So this equals 1/4. And that's like saying 1/4 of your deck is hearts. And that's true. 1/4 of the deck is, in fact, hearts. What about the King of Hearts? You guys ever hear that phrase? Maybe not. You might have heard Queen of Hearts. This is similar. This is the King of Hearts. So if you say, what does that mean? You're a king and you're a what? Heart. That's really what that means, to be a King of Hearts. So I need to know how many cards are kings and hearts out of the 52 cards, because this is again N of S. Okay, so what is it here? What are you guys going to say? Well, there's 52 cards in the standard deck, right? I got to look for a card that's a King of Hearts. So if I look at the king column there, that first card is a heart. Are there any others? No, there's a King of Diamonds, there's a King of Spades, and there's a King of Clubs, but there's only one King of Hearts. There you go. All right, easy breezy, lemon squeezy here. All right, what about that hard question here? How many red cards are there? Well, let's see. I'm going to do it this way. Here's going to be the probability of selecting a card and it being red. We got to know the total number of red cards in the deck divided by the total number of cards. I already know there are 52 cards in a standard deck. Okay, so this would be 52. N of S is the same for all these questions. Now, look at the deck. How many cards are red? All the hearts are red. All the diamonds are red. We know there's what? 26. Oh, I'm sorry. I made a mistake on that one. You were right. I was so confused too. It's not red cards. I typically ask the red card question. 26 out of 52. But I didn't. I asked a red king. Okay, so how many red kings are there? There are two. What are they? The Queen of Hearts and the Queen. I'm sorry, the King of Hearts and the King of Diamonds. There's two. What does that reduce to? 1 out of 26. Okay, the standard deck is very rich in examples. This is why it's commonly used. Okay, so we have you guys try some on your own. I'm going to say here question number 5. Chance you select a black card. Question 6. Let's move this out of the way. I'm going to say a card less than 5. 7. A card. Say a red card at least 8. And number 8, what should we say? Chances with the ace of spade. Okay, I'm going to give you guys some time to answer this question, or these questions, and see what happens here. Okay. All right, let's try this out here. And say, what's the probability? So question number 5. Probability of selecting a black card. We have to know how many black cards are in the deck out of the total, right? So number 5 here. We know there's 52 cards. How many cards are black? Which are the black cards? The spades and the clubs. So there's 26 here, 13 and 13. And then this reduces to, of course, 1/2. So ladies and gentlemen, there you go. Probability. Okay, number 6 now. A card less than 5. So I'm just going to put the answer here. I know the bottom is 52. Okay, N of S, 52, 52. That's always in the definition, right? So how many cards, what are they saying? The card has to be less than what? 5. What does less than 5 mean? Strictly smaller than 5, right? So in this case, it's 4, 3, and what? The 2. So what is that? 3 times 4? So that's 12. You know what that reduces to? That's 6 out of 26. 2 goes into 12 6 times, right? 2 goes into 52 26 times, and 2 goes into 6 3 times, and 2 goes into 26 13 times. Ladies and gentlemen, there you go. Probability is 3/13 here. All right, number 7 here. A red card that's at least 8. A red, it has to be red. This will be over 52. And it has to be at least 8. What does at least 8 mean? It means 8 or more. So it's 8 or what else? 9 or what else? 10 or a jack or a queen or a king or an ace, ladies and gentlemen. At least 8. 8, 9, 10, jack, queen, king, and ace. Notice if the ace is low, I wouldn't count it. So wherever the ace is at, that's a factor. Is that right? So we got 8. So I got 1, 2, 3, 4, 5, 6, 7. 7 times 4 is what? There's 7 cards of each type. That was 7 times 4. Because at least 8 means 8 or more. Is that true? So let's reduce this fraction. 2 goes into 28 14 times. 2 goes into 52 26 times. 2 goes into 14 7 times. And 2 goes into 26 13 times. So ladies and gentlemen, here you go. 7 out of 13. Huh? Oh, and then it has to be also red. So what does that mean? It's not 18, it's what? Half of those are red. So of the 28, so it's really 8, 9, 10, jack, queen, king, ace. That's 7 times 2, which is what? 14 there. Okay. 2 goes into 14 7 times. And it does not reduce anymore. So good job. Don't forget, number 7 was red cards that are at least an 8. So half of those are red. It's not 28, it's really 14. Has to be what? Red cards that are at least an 8. Yeah. See, you don't want to sit way up there. You got the best seat in the house. Ace of spade. What's an ace of spade, ladies and gentlemen? Number 8. See, an ace of spade is a card here. Let me get rid of this picture. It's a card that's an ace and a spade at the same time. There's my spade. So I know there's 52 cards in the standard deck. How many of those 52 cards, though, is an ace of spade? What's the ace of spade? It's in the lower right corner. How many of them are there? You say, I see another ace. That's an ace of clubs. It's not it. It's an ace of diamonds. It's an ace of hearts. There's only one ace of what? Spade. One out of 52, ladies and gentlemen. So what do you guys think? Is the standard deck really that big of a problem? Right? It's not a problem if you draw a picture of the deck and you know that picture. It's not a big deal. All right, let's give you guys another definition here now that you guys have a good dose of probability. Definition of what we call the what? The complement of an event E. Okay. And the notation is this. You see it in different books. E with that line, E with the power C, E with a prime power, or simply the phrase non-E. This is all notation for the definition of the complement of a particular event. Okay, so this is going to be a big, important definition for us, complement. Okay, this is the following. It's the outcomes that are not in E. They're not in E, but they're still in the sample space. That's the complement of an event. Ladies and gentlemen, this is the complete logical opposite of E. Okay, this is an extremely important definition and big deal. The complement of an event E. It's the logical opposite. It's very simple, but some people make it harder than it has to be. Let me give you an example. Logical opposite. If I said to you, what's the logical opposite of up? It's simply not up. Let me say that again. I know. See what I'm saying? It messes people up. What's the logical opposite of up? Not up. What's not? It's exactly. It's anything but up. So you might say, is it down? Well, is it to the right? Yes. Is it to the left? Yes. Anything that is not up. Okay, you guys, that's a big deal. There's a fine line there, okay? Like, if I said to you, for example, this is something that people often will get confused with as well. If you guys want to know, what are the political parties in the U.S.? Where are the poli-sci majors? Well, be careful. Be careful. You might say, Mr. Judge, Democrat. Okay, what else? Republican. You also have what though? It's not just two parties. You got the what? Green Party. You got the Independent. Right? What else do you guys have? Peace and Freedom. PNF, Peace and Freedom. Any other parties? Libertarians. What else? You guys know what I'm saying? Huh? There's actually quite a few, I think. Libertarians, Peace of Freedom, Independent, Green Party, Socialist Party, Communist Party. In the U.S., are the Communist Party members? No? I think so. Well, yeah, I mean, I'm going to say to you guys, Mr. Judge, let's see if you can guess my political party. Mr. Judge is not a Republican. So what is he then? Don't say he's a Democrat. It is anything but a what? Cross out the Republicans. What could Mr. Judge be? He could be a Democrat. That's possible. He can also be a what? Green Party. He could be independent. He could be Peace and Freedom. He could be a libertarian. If all you know, he's not. He's a non-Republican. These are all the non-Republicans. Non-R. Notation-wise. R with a line. R with a prime. R with a C. My favorite notation you guys will see me use is just these two. But there's other books that have R prime and RC, you know. That just means complement of the event. So if you're talking about being a Republican, what's non-Republican, you're a Democrat or Green Party or Independent or Peace and Freedom or Libertarian. So don't think people are just either Republicans or what? Democrats. They're not. They could be others. Anybody here part of another party by any chance? Is everybody here registered to vote? No? Yeah, how old do you have to be to vote? 18? All right. Then you have to serve in jury duty. Anybody here serve in jury duty before? How do you like it? It's weird. Yeah. You do that for a whole week? And, oh, okay. Well. I wouldn't want to do it. Huh? How do I get out of it? I shouldn't tell you guys. I never go. I just don't even show. That's what they say. $5,000 fine? Oh my God! I better. That's why I didn't want to tell you guys. I don't want to tell me the penalty. Anyway. Okay, let's shake that thought out of our head. Let's get out of there. No. All right, let's see. What was my original question? Let me ask you guys this question. Remember the standard deck? We'll say question number 9. Probably select a non-king. Question 10. A non-club. Question 11. A non red card, non and complement. Okay? That's horrible. Probability of a non-king. What do you think the card has to be? Anything but a what? Anything but a king, ladies and gentlemen. N of S, what's that going to be? 52. So what we got to know for number 9, a non-king, we have to know what is a non-king. It is everything but a king. Is that true? You know how I figure this out? I say there's 52 cards in the deck and I subtract the kings. You guys with me on that? Out of the total number of cards, out of the 52, we throw out how many kings? 4. How many non-kings are there? 48 non-kings, ladies and gentlemen. This is how we start to think about that, okay? So, can I reduce that? Remember, you keep dividing it by 2. The top and the bottom, 24 out of 26. Can I keep dividing both by 2? Okay, this would be 12 out of what? 13. And ladies and gentlemen, you computed the probability of a complement of an event. Important thing. Okay, so any card but a king. Look at number 10, a non-club. How do you think we do that one, non-club? Let's see. Probability of a non-club. What's that going to be? I know by definition it's the number of non-clubs out of the total number in the sample space. So, 52 cards in the standard deck. How many cards are not clubs? Right? So what I'm going to have to do is the same thing. I'm going to look at this deck. I know out of the 52 cards, there's 13 clubs, aren't there? So that means this is now the non-clubs. Throw out the clubs. That gives you what? 39 out of 52. Okay? Now, believe it or not, both of these numbers are divisible by 3. 3 goes into 39 13 times. 3 goes into 52 how many times? You might say, I don't know. We'll get out the TI. Remember how to clear that? Second quit. 52 divided by 3. Oh, wait a minute. It's not divisible by 3. Sorry. So how do we reduce? Let me go back to the iPad. Oh, I think 39 is divisible by 13. And it's also, 52 is also divisible by what? 13. So 13 goes into 39 3 times, and 13 goes into 52 what? 4 times. You might say, I don't believe you. Okay. Let me scroll out, by the way. 39 divided by 13 is what? 3. 52 divided by 13 is what? 4. They're both divisible by 13. So this reduces to what? 3/4. Okay? Where's the iPad? So there's our probability. A non-red card? What does that mean? Anything but red. So in other words, probability of a non-red, how many cards are non-red out of the total? What's that going to be? 26. If you're non-red, what does that mean you are? You're black. 26 out of 52. Okay, let me move this out of the way. And then that reduces to what? Well, reduces to 1/2. Right, 26 is divisible by 26 one time. 52 is divisible by 56 twice. So this is how we look at this here. So it's good to study that deck because it helps us answer some nice wet probability questions. Now, let me give you guys a definition here. It's a pretty good and important definition. Has anybody ever gone to Vegas by any chance? Anybody here, actually, you guys like going to Vegas over there, you two? Since you were what? 9. What'd you do when you were 9? Wax Museum? Who'd you see? Donald Trump? Marilyn Monroe? Wax versions, the Beatles? You in the Circus? So what do you guys do when you go to Vegas? Play war? What's that? I have no idea. Is it cards? Oh, I have no idea. Okay, so what do you do? Ace is the highest? King is higher than Jack, okay. So, I gotta look that game up. I gotta look it up. So you gamble on that one, huh? Anybody out? What do you guys here? Anybody here gamble? Nobody here gambles? You're too young to gamble? Does what? What is that? All of that? Oh, I know. I've seen it. Oh my God! You guys, let me see. Let me see. Oh my God! You got the T-shirt. I guess I've played that game before. I've played it before. Miners gambling, but what do you win? Flamin' Hots? Plays for money, yeah. All right, pretty good. Okay, well, let me express this to you guys. The reason I'm bringing up gambling is because I should say to you guys, there's another measure of chance that's very, very popular. It's not just probability. You ever hear the words odds? This is another, ladies and gentlemen, measure of chance. So if you go to Vegas, you know how they communicate likelihood and chance? They don't say probability. They use odds, ladies and gentlemen. You say, what do you mean? They use odds. Well, let me give you the definition of odds for an event E. There's two definitions of odds. I think Vegas uses odds against. Odds against an event E. Odds, ladies and gentlemen, this word. So it's a ratio, just to let you guys know. This is N of E 2. There's that word 2. Remember that? To N of non-E. This is the definition of odds for an event. Okay? And odds against an event is the opposite. In other words, this is the ratio of N of non-E 2. That's what that symbol means, to N of E. Okay, so this is odds against an event. Now remember, I'm going to get out this red here. Non and what? Non. There's not P. There's no P. What does P stand for? Probability. What does this N stand for? Number of, cardinality. Okay, so you're going to have like an event here. Put it there in green. Just in other words, these are ratios. They don't use, ladies and gentlemen, probability. They use these two ratios. In fact, Vegas uses odds against, so you guys know. But sometimes you just see the word odds. You go, which one is it? Odds for, odds against. Vegas, odds against. That's the gambling measure of chance. Okay? It's kind of like this. N of E here is thought of as, I'm going to write down these words, the number of successes. N of non-E is thought of as the number of failures. So it's really the number of successes to the number of failures, or you can look at it the opposite. Number of failures to number of what? Successes. So it kind of brings me up, and again, these are ratios, and it's an extremely important idea. It kind of brings me up to the idea. You guys ever see the movie Dumb and Dumber? It's one of my all-time favorite movies, Dumb and Dumber. You haven't seen that? You never even heard of it? You're gonna have to sit your mom down, you and her, and watch Dumb and Dumber. You're a Pokemon? Oh, Dumb and Dumber is like a classic. Is Dumb and Dumber from the 80s? It's in the 90s. You guys ever see it? You're going to say, I wasn't born in the 90s, Mr. Judge. You forgot it. Jim Carrey. And anyway, it always reminds me, it makes me laugh when I hear this, because it's actually true. It's ironic. There's a scene, if you guys know about Dumb and Dumber, it's all about Lloyd Christmas and who's the other guy? Lloyd Christmas, what's the other guy's name? Perry? You have to look it up. Anyway, they're both in love with the same woman. You guys remember that one? What's her name? You guys don't remember? What's her name? Her real name is like Holly Robinson. But what's her name in the movie? I don't think so. It's not Holly. I have to Google it. Dumb and Dumber. I'll remember it. What are their names here? Dumb and Dumber. It came out in 1994, by the way. The plot. What's the plot? Lloyd Christmas and Harry Dunn. Okay. That's the two. They Mary Swanson. There you guys go, Mary Swanson. Okay, you guys remember that? So they're both in love with Mary. They're kind of fighting over her. And turns out she's married, yada, yada. So at the end of the movie, they try to save her from these bad guys. And they took all this money, ran some money. If you haven't seen it, sorry to spoil it for you. But at the end, Lloyd Christmas approaches Mary Swanson and says, so what's the chances of you and I getting together? Do you guys remember what she said to him? She gave him odds. You know what she said? This is her answer. 1 in a what? Million. All right. 1 in a million. That was odds. That's 1 to. There we go. 1 to 1 million. She gave him odds. There's one chance to 1 million chances. That's odds 4. Okay? So there's one success right in here. One success to the what? The 1 million failures. And he looked at that statement, and what do you think he said? Did you remember what he said? Yes, he started smiling, he got really happy, and he said, "You're telling me I have a chance." Yes. Now, the funny part of that whole premise is he's actually right. There is one chance. But there's also out of what? Out of a million chances. So it describes, that's called the odds. You're right, odds 4. So every time I hear it, I laugh, and I'm like, oh my God, she gave him odds 4, and he didn't. She was trying to tell him nicely, like there's no chance. But what he said, what she said was actually very true. There's one chance. You know, so it's kind of interesting. Anyway, every time I hear it, it just makes me laugh. Every time I see it. I don't know, maybe you guys don't get there's only a few of us get the joke there. It's a hilarious movie. Okay, so if you guys ever have a Netflix night, you can watch Dumb and Dumber. But don't watch Dumb and Dumber 2, just watch Dumb and Dumber. It's called Odds 4, ladies and gentlemen. Okay? Now, let me give you an example of how to do this, because it's another measure of chance. I mean, if you go to Vegas, they're going to talk probability. They're going to talk odds. So this is odds 4. You know what she could have said? The odds against? I'll put it in purple. Just say it backwards. 1 million to what? 1. So there's 1 million failures to 1 success, or 1 success to 1 million failures. It's still communicating the same kind of thing, so you guys know. So there's just 2 definitions. Odds 4, odds what? Odds against. Okay, we're going to be computing some odds. It's very simple, but what I'm going to do now is I'm going to give you one of my favorite examples, which is going to be a bag of marbles. Give you a simple kind of example. And there's always a debate. How do you guys spell marbles, by the way? It's like marblez. It's like marblez. You guys know? It's like a French word. Sometimes people say, no, it's not. It's marblez. Marbles. Oh. Marrows. We need a B. Marbles. Marbles. You got a bag of marbles. Anybody play with a bag of marbles before? Let's say you have maybe 8 red marbles, 4 yellow, 2 green, 1 blue. If you select a marble at random, what's the odds for selecting question 1? Red. So we're going to go through it together. Okay, so over here, 8 red, 4 yellow, 2 green, 1 blue. This is what's in the what? Bag. Okay? All right, you guys okay with that? Let's go through the definition. Here we go. This is the definition of odds what? 4. Odds 4? So how do we do this? What's the definition? It's a ratio. Number of red number of non-what? Red. Sorry. So you just have to go back to this bag and be able to do what? Read. It's not even counting. You know why? They counted it for you. How many red marbles are in the bag? Good job, 8. Okay, you say, how do you know? Right in here. I told you there's 8 marbles. Now, how many non-red marbles are in the bag? No, you say, how do I know? That probably you have to count, right? You might say, okay, 4 plus 2 plus 1 is what? 7. So this is 8 to what? 7. This is the odds for selecting a red marble. All right, easy breezy, lemon squeezy. You guys okay with this? Odds for selecting red. Okay. Give you another question. Odds for, did we say, we'll try yellow. What's the odds for selecting a yellow marble now? Okay. What's your definition? Number of yellow marbles to the number of what? Non-yellow. So how many marbles here are in fact yellow? You say here they are. 4 yellow marbles. Okay, you're using the definition of odds 4. 4 yellow marbles. And then how many non-yellow are there?
11.
How do you know there's 11? Well, you can count the rest, or you can do something like this, right? You can say, hey, what's the total?
15.
There's 15 marbles in the bag. So if you said there's here, this is like 15 minus 4. This was like 15 minus 7. Is that right? So you could use the fact that you know the total if you have the total. Very easy ratio. It's extremely important ratio. What's the odds for selecting green now? Use the definition. Right? It really comes down to, do you know the definition? Number of green to number of what? I would even recommend writing down the definition. It's my recommendation. Because then you learn it. So how many green marbles are there? Good, there's 2. There's 2 green, there's 15 total. So you can say 2, and then this other is going to be what? How many non-green are there? Say 15 minus 2 gives you what? 13. So there you are, ladies and gentlemen. You got these odds 4. These are chances here. Okay, now question number 4 here. Odds for selecting green. We're going to say odds for selecting blue now. So use the definition of odds for the number of blue to the number of non-blue. How many blue marbles are there? 1. And then how do you get the other one? 15 minus 1 is really what going to be again? It's 14. So this is like saying there's 1 success to 14 failures when you're going to select blue marbles. 1 success to 14 what? Failures. Does that make any sense to you? 1 success, 1 in a million, 1 success to a million failures. These are better odds. 1 to what? 14. What is this? 2 to what? 13. 4 to 11. 8 to 7. You want to know something interesting about this answer here? This answer is a nice answer. Do you guys know why this is kind of nice to think about? 1 success to 14 what? Failures. You guys want to know why that number 4 is really nice? Because it's in the form of a what we call a unit ratio. You know the meaning of the word unit? You know what that means? It's there's a baseball player, let's see if you guys know. He's called the big unit. Who am I talking about? Who's the big unit? Looks like a number 1. That means he's tall and skinny. You guys remember the big unit? Randy Johnson, the big unit, okay? Looks like the number 1. So the reason this is nice is, and this is a unit ratio, is because you see this number here in the first position? 1 is like a nice whole number. We understand that better, like 1 success to 14 non-successes, 14 failures. We understand odds that way with that unit ratio. Do you guys know what I'm saying? Like if I said compare that to 2 to 13. 2 successes to 13 failures. Doesn't have an impression on us. 4 successes to 11 failures for selecting a yellow marble. 8 successes to 7 failures. So here's what I want to remark. Here's going to be something you care about. Ooh, got rid of it. I want to say here's a fact you want to care about. We can unitize our ratios. Okay? In other words, this ratio of A to B can be, what was that word again? Yeah, Randy Johnson, the big unit. Tall and skinny. Number 1. Here's how you do this. You guys know you can simplify any ratio? Do you guys know that? By dividing both of the numbers by any non-zero number? You can simplify a ratio. So what I'm going to do here is this. I'm going to divide both of those numbers by that first quantity, A. Okay, now what is A over A? Yeah, it cancels out, becomes the number 1. And so now this is B over A. Now here's my point. Didn't we unitize this? First quantity. We unitized that first quantity. It's now a unit ratio. So if I wanted to unitize any ratio so it makes better sense to us, like this first one, you see the green here? I can unitize. How do I do that? Divide the first number by 2 and the second number by 2. They have to be the same number. What does 2 over 2 become? 1. Good. Unit ratio. 1, 2. And then what's 13 divided by 2? Do you guys know what that is? That's 6.5. If you don't believe me, the TI is here. And 13 divided by 2, you can unitize your ratios. 6.5. So you might again say, why do we care about unitizing ratios? Because we could now communicate a lot better. We can now say there's 1 success for choosing a green marble, and then 6.5 what? Failures. 1 to 6.5. It's okay to have a decimal. 1 to 6.5. It's okay to have a decimal. Approximate that to the tenths. If you ever look at baseball odds, you might see a decimal. Like the chance the Dodgers win the World Series. Maybe you care about that. If you go to Vegas, you might even see those odds there. 1 success to 2.2 failures. It's a decimal representation. Okay, you guys okay with that? This is unitizing those odds. It's a better way of thinking about what's happening here when you unitize. So for yellow marbles, 4 successes to 11 failures. You can unitize this. You just have to know what 11 divided by 4 is. This is 1 success to, what's 11 divided by 4? Do you guys know? Let's ask the TI. 11 divided by 4. What happens here when I unitize? 2.7. I'm going to keep it to the nearest hundredths. Sorry. Just kind of nice and neat. I can go to the tenths. I can say 2.8. All right, let's go to the tenths if you want to do that. Let me go to the iPad. Approximate this to the tenths. It's 2.8. Ladies and gentlemen, we now have the odds for selecting a yellow marble. There's 1 success to 2.8 what? Failures. That's almost 3. This is how we look at odds. Yes?
I got a question. For number
Mm-hmm.
6.5
You might want to keep it to the nearest tenth so it's a little more accurate. Versus saying 7. I mean, you can, but typically people try to leave some decimals just for accuracy. Like, it's a very good question. The real answer is this. It depends on the topic. Like, for example, when we were looking at yesterday, finding the percentile, that procedure, round up, that's based on the process. Odds, I mean, you might go to the horse races, and they have this to the nearest hundredths. And so you go, what happened? What did they do? Well, whoever computed that decided to be a little bit more accurate. Or maybe they go to the tenths. So it's really based on whoever's computing, and there's not a rule other than saying, like, for example, things that I've seen in a gambling scenario in Vegas is like to the nearest tenths or hundredths. So that's just based on tradition, more or less. So, I mean, yeah, you might go to, like, I'll even say, if you're a baseball fan, and I am, right, I love baseball. New York, you ever watch, there's a lot of people watching sports games in New York, really in all the casinos. But New York, as soon as you walk in, there's those cameras with all these sporting events. And you can even get a pamphlet. They teach you about how they do what they do. And you'll see, oh, they go to the tenths. Oh, they go to the hundredths. You might even read online, and it happens all the time. Chance of the Yankees winning the World Series. Chance of the Dodgers. Chance of whoever. It's going to be in language of odds. It's not in probability. So it's by tradition is the short answer. So typically you might say, what about for me as a student? And hopefully whoever writes the question will tell you. So say approximate the answer to the tenths, approximate to the hundredths. You can even unitize this, the chance of selecting a red marble. The odds for selecting red. It's 8 to 7. Unitize that first number. So you divide both numbers by 8 and see the difference now. Now, ladies and gentlemen, yes, that first answer is going to be a what? A 1. But 7 over 8, we got to go to the TI, right? So 1 success to 7 divided by 8 now, failures. Now this one, you go, this is 0.875. Well, you can see 0.875. That's just the exact answer because that decimal is exact, 0.875, right? So, if you went to Vegas and you said, what are these odds here? 1 what? Success at 0.875 failures. Well, that's not quite 1 failure. It's not like the others, right? 1 success to what? 2.8 failures for selecting a yellow marble. Over here, 1 success to 8.75. They can even round to the nearest tenths and say, well, that's 0.9, 1 to, oops, we need that semicolon because that's the word to, 1 to 0.9 failures. That's not even quite one failure. So it still communicates chance and likelihood, this definition of odds for. So you got odds for, you got odds against, you can unitize that quantity, first quantity, and now you're better able to think of the chance of something over it being a probability. But this is odds, ladies and gentlemen, and unit odds. So let me give you guys some more odd information, unit odds. If you're into dating or you want to get married, people do. Okay? There's a ratio of men to women. Okay? The ratio of men to women. I mentioned marriage and people leave. Anybody here want to get married? I've got some advice for you. Don't get married. Okay, get married if you want. You can get married. It's not a big deal. I say wait till you're 50. I have a friend. He waited till he retired. He was like 72. It makes a lot of sense. I think about this friend of mine. He's actually our former department chair. I won't mention names. He when he got married, he retired. It was like years after he retired he got married, like maybe 5 years or something. I'm like, you're getting married? Yeah. Makes sense. Makes a lot of sense. I don't know. Well, let's talk about the ratio of men to women. You guys know it. See if how you like these odds. There's 1 man to 3 women. Where do you have these odds? Australia. I was told Australia. Yeah, it does explain a lot. Yes, it does. Australia. There's 1 man to 3 women in Australia. So I hear. So if you're a guy and you're interested in getting married, where do you go? Australia. You got 1 guy to 3 women. That's like you can have a date every night of the week if you wanted. You guys know what I mean? I don't recommend it, but if that's what you want, I don't recommend it though, because that's asking for drama. So you might say, I'm a guy and I like those odds. Okay. Just kind of an idea about odds. Where do you go where this is reverse? There's 3 men to every 1 woman. Now you ladies might say, okay, I like that better. I like that better. You're trying harder for me. You guys know what I mean? You 3 guys are working hard. And women like that. You guys, ladies like that? You like these guys working hard for you? No? You guys know what I mean? You guys know what I mean. Put in the work. No? You don't like that? You don't want the guy working hard for you? Yeah, why do you need a guy anyway? Good thinking. Who cares? Huh? Waste of time. You got that right. These guys are a waste of time, aren't they? Anyway, if you all opinions are good opinions, ladies and gentlemen. Australia. Where do you find the reverse of this? I'm not sure. Could be. It might be close to that. I know it's in Alaska though. It's a state. Spain's a lot. Yeah.
So what about places where they have like 8 wives?
Uh, well, that's a little bit different. That ratio might be a little bit different. That's like a ratio of a married, a husband to a wife in a what's called a polygamous, setting. Um, Utah used to do that. In Arizona or Utah? You sure it's Arizona? She moved there. Did she meet a nice Mormon boy? But he expects, you're saying he practices polygamy? Well, I didn't know that. Yeah, I don't know. I think so. I don't know a lot about it, but I think it's transparent. I think it's understood. It's supposed to be understood. Supposedly, it's not practiced because it's illegal. Even I don't think you can claim religious. Um, I don't even think you can claim it's a religious right. In all honesty, polygamy. But I might be wrong. I have no idea. I thought you can't do it anymore, but maybe I'm wrong.
They're not recognized by the
Yeah, there's going to be an issue. I don't know. I would think there'd be a lot of issues. I think there'd be a lot of problems, right? How many? Anyway, I can't even say it now these days. Can you have more than one lady in the kitchen? Can't do that, right? Imagine you have more than one wife. I don't think that's going to work out very well. Does that work out well? I don't think that works. I have no idea. I don't even know I don't even know why you need more than one wife anyway. Why would you need more than one? Imagine Christmas. How many Christmas presents you got to get? That's what I'm thinking. That's what I was saying. That's what I was saying. Imagine all the arguments in the kitchen, and oh my God, forget it. You never listen to me. Which wife is saying that? All of them. You never talk to me. You never listen to me. All your wives are saying that. You want to live that way? I don't think I want to live that way. Horrible. Anyway, there are ratios that are again they're interesting, and yeah, China does have an issue about the men to women ratio. I don't think it's 3 to 1 though. But history has shown, in case you guys didn't know, in history, whenever there's more men than women in a society, that's a violent society. They will fight. Men will fight, historically. So people study that kind of ratio of men to women and see the effects of it. And I guess, men, I don't know, men need women, or it's about marriage, it's about having a family, whatever it is, right? Having children. You can't really easily share a woman like men can share a man, if that makes any sense. You can't have that polygamy situation where it's reversed so easily. Maybe. But you're going to see in polygamy, you're going to see the other one. You're going to see there one guy to many women, not the other way around. Those ratios. What do you guys think about that? It creates what? I think it just is, well, I don't know. If you're maybe in that situation, maybe you should ask your cousin in Gilbert, Arizona. See what she thinks. See what she thinks about the situation. Maybe she thinks it's weird. You got to ask those ladies and see how they think. I don't know how they maybe I don't know how they rationalize it, justify it. Maybe it's a religious thing. Yeah, I think there's probably I can sense a lot of problems. multiple relationships? Oh, in that situation, there's no lying, there's no cheating, so there's no betrayal. I would think it's a mess. But I'm not in that situation. I don't even think I want to be in that situation. I go home and I get 3 wives yelling at me. No, just one. Got all 3. You go in one room, somebody's yelling at you. You go in the other room, she's yelling at you, the other wife. You go, I'm getting away from that one. Going to the next one, she's yelling at you too. Yeah, they probably work as a team. It's a team, right? So they're like, let's be mad at him today. Okay, we'll be mad. Let's not be mad. Let's not be nice to him today. You guys know? Is that kind of how it might work? You guys don't know what I'm talking about? That's how I'm thinking how it works. They sync and they gang up on the guy. I told you we wanted a new kitchen. I'm like, okay, I gotta get started on the kitchen. And they go, okay, I'll get they're all mad at you, so you gotta get the new kitchen. Say, hey, look at this sofa. I've been telling you I want a new sofa for quite some time. Gotta get a new sofa. Imagine they get the whole wife team after you. No, they all sit you down and say, we want new couches. No, I think they're all on one roof. Aren't they all on one roof? They're all on one roof. It's not separate houses. They're all in one house. And they're probably saying things like, there probably is a hierarchy. Like, this is my main wife, and these are the side wives. You guys know what I'm saying? There's probably the main, and then there's the side wives. That's my guess. And you got 12 kids. What does that make the kids? Brothers and sisters? Half brothers or something? Half brothers and sisters. So they're still related? I don't know. What time is it? Anyway. There's a show on that on TLC. Thanks, Kimberly. I'll take a look at that show. I'll take a look at the show. Thank you, Kimberly. Interesting. I'm glad people are still with us. Anyway, I was going to give you guys a break, but let's take a look at let's take a look at our assignment portion here so far. Let's go back. I don't even think I want to watch the show. You get to the point where I don't think you even want to see that stuff. Like, So let's take a look at this one here. So some of you guys say, what do we do? Believe it or not, we're not done with Statistics Lecture 5. We have a lot. Oh, we are kind of. Look at that. Statistics Lecture 5, probability, odds, and the complement. I think I want to give you more examples, though. But you can get started as much as possible. And yeah. And then I'm going to go over here. And I'll take this out here. There's also something else I want you guys to see here because I have it, and I'll put the link. Unit odds for an event. Got some homework here. So I got homework on unit odds as well. Let me see. Yeah. The unit odds thing. So you guys say, hey, what about this? If you say, what about, I think I have solutions here too. For unit odds, it's right here. So if you get stuck on those, that's weird. Yeah, I do have those solutions. Let's try to put that in there. I don't know what that is. So you might go, well, what is this? These are the solutions here. Anyway, it looks like okay. It looks like we have some work that can be done. Of course, we're gonna do some more things tomorrow. What time do we get out of here? Do you guys know? Oh yeah. Let's give you some definitions here. No, there's a supplement part. So let me give you guys some important definitions, and then we can get out of here. You got your stuff. Then we could get out. So here's the definitions, okay? So you guys want to get these so we can start communicating. Definition of, we say this. What do we say? Oh. Two events, E and F, are equally likely if they have the same probabilities. So there's two events here. One called E and one called F. Remember, if they're equal, we say they're equally what? Likely. Equally likely. Okay? That kind of makes some sense. You guys think about it that way? Definition. We say E is more likely than F if the probability of E is greater than the probability of F. So, let me do something here. The context here is two events. Say, are equally likely if P of E equals P of F. We say E is more likely than F if it has a greater probability. So the context is here is in two events here, E and F. Okay. Definition. We say E is what? Less likely than F. Less likely if P of E is less than P of F. Probabilities are smaller. E F, so I'm going to get the keyword here. More likely, there's the greater than inequality. Less likely, there's the less than. Okay, some fundamental definitions comparing two probabilities. So very often I'll start using language like that, more likely, less likely. Okay. Here's a fact about probability. For any event E, probabilities live between 0 and 1. So you got an event, any event, okay? So you don't have any such thing as a probability that's greater than 1 or negative. You can't have a probability value of 2.5. They're between 0 and 1. There's your E. And here's another very important definition. We say an event E is impossible. Okay, this is the definition of impossible. If your probability equals 0. Not close to 0, has to equal 0. Okay, this is what it means to be impossible. The chance equals 0 for that event, the probability of that event. So if it's equal to 0, it's impossible. It means it can't happen. And we'll see some. Definition, we say an event E is certain if the probability equals 1. So some important definitions. This is the definition of being certain. Okay, it has to equal 1. So if you can ever compute a probability and it equals 0, we know that event is impossible. If you compute a probability and the event is 1, we say the event is certain here. Okay, I want to put this fact here. Okay, two more definitions here. Definition. We say an event is almost certain. Almost certain. If the probability is quote unquote close to 1. Okay. You say it's almost certain. So that event has to be close to 1. Now you might say, how close? This is how close. It has to be bigger than 0.95, 0.95, but certainly less than 1. This is how close. This is how they define close. I think it's like at least 95%. But it's not certain. So this is what they mean by being close. These are all language we use when we start talking probability. Last definition of the day, definition. We say an event is, this is almost certain, I will say is not likely. It's not likely to happen if the probability is, again, quote unquote, now close to 0. So that probability is close to 0. And then you say, well, what do you mean by close? What is close? It's like less than 5%. So you might say the chance is, I think it's less than or equal to 5%, which is 0.05, but it has to be bigger than 0. Otherwise, that we would say it's impossible. So these are nice definitions that really allow us to start to communicate with probability. Like, winning the lottery is not likely. That probability is close to 0. It's still possible, which is why I buy tickets. I buy lottery tickets, still possible. But it's not likely I'm going to win. Probability is less than 5%. Okay, you guys okay with that? Those are kind of some things that, just to let you guys know, the language with these definitions are important. So I did want to get these definitions in. I know they're probability definitions. They're not odds definitions, but you know. We got some good fundamental work in, okay? So we're going to continue with probability when? Tomorrow morning. All right, yeah, we're going to continue with that. So I hope to see you guys tomorrow. Stay safe and have a great rest of the day. Bye, take care.